So let's pick up where we left off last time. Last time we introduced the two-dimensional signal. We assume that you have two vectors which are orthogonal and they form the basis of a vector space or signal space. And let's continue with that today. So I guess the title will be two-dimensional signal. Okay. Once you pick the two vectors, then you can form any of your signals in a signal space as a combinations of these two vectors. Let me give you a couple of examples, and then we generalize and look at two broad categories of the signals. Let's say, first example is something like this. This is now psi1, psi2, two orthogonal vectors. So I know that if I would take the dot product of psi1 and psi2, I get equal to 0, and then norm of psi1 is the same as norm of psi2 is equal to 1. Then I can pick I can pick the signals in my signal set as essentially points in this space here, which let's say I pick them this way, and I call them like this. This is S1, S2, S1, S2, S3, and S4. So what that means, I form my vector S1 and the corresponding signal as, I guess, square root of, let's say, this here. We know that this is square root of energy. And since all of these are essentially on the same distance from the origin, the energy of all of these signals is the same. So I can say that this S1 is square root of energy. Make sure that I have here only 2, but I don't know where 2 is, so let's assume it's here. And square root of energy over 2. And then S2, which is this guy here, is square root of energy over 2 minus square root of energy over 2. S3 is this guy over here, so this is minus square root of energy over 2, square root of energy over 2. And S4 is minus square root of energy over 2. Minus square root of energy over 2. This is in a vector space, and you can see that this is a relatively simple notation. Now, we don't really send vectors, we send signals. So what this means is there are essentially two signals, psi1 of t and psi2 of t, now that are waveforms, the signals in time. And this translates into integral over signaling time of psi1 magnitude squared dt is equal to integral over signaling time psi2 of t magnitude squared dt is equal to 1. And then what this means is I form S1 of t as square root of energy over 2 times psi1 of t plus square root of energy over 2 times psi2 of t for t between 0 and t, for example, the signaling interval. And likewise, I form all of these others. This is what actually exists, right? I pick two waveforms and I make sure that they're orthogonal, which translates into integral over signaling time, psi1 of t times psi2 of t is dt is equal to 0. This is what actually happens in the time domain. But this is how I'm going to see this in a vector space domain, where I'm going to treat these two as orthonormal vectors forming the basis of my signal space. And then every point that I signal with is going to be a combination of these two basis vectors. So I can extend this, and you can see that this is a relatively simple combination that I can pick up. I can look at some alternative ways of doing this. If I want to increase the number of symbols in my signaling set, I can do something like this. Pick maybe 8 of them. Or nothing restricts me from doing even something, you know, like this. Have and so on. You can envision that there are multiple, or at least many different ways, infinitely many different ways, how I can pick all of these points in my signaling space. There are, in practice, two principal ways how we actually pick these points. It is going to be, later on through course, we're going to explain why, we'll add some explanation when we talk about amplification, a little bit of explanation when we talk about the noise and so on. But in principle, we have two ways how we pick these points in our signaling space. There is one way which we call phase shift keying, and there is another way which we call quadrature amplitude modulation. So let's first talk about phase shift keying. So I guess two-dimensional signaling. And this is phase shift keying. Phase shift keying, or PSK. The signals in PSK, so signal, before I go any further, right? So far, we've been talking about this psi1 and psi2 being any two orthogonal signals. In principle, that's, there is nothing in theory that requires for them to be anything particular, except that they need to satisfy these two conditions. They need to be orthogonal to each other, and they have to have a unique norm. The practical choice for psi1 and psi2 is this. For psi1 of t and psi2 of t, psi1 of t, we usually pick as a cosine 2 pi f0t, and psi2 of t, or rather 2 cosine 2 sine 2 pi f0 of t. And you can see right away that they meet both of these conditions. Sine and cosine are orthogonal with respect to each other. If you pick this t judiciously, then they're strictly orthogonal. If t is much larger than 2 pi 1 over f0, then they're orthogonal regardless of what the t is. So these two signals by far are the most common choices for these two orthogonal basis signals. So if I look at PSK signal, the PSK signal has the format that looks like this. Um of t is going to be equal to gt of t times cosine 2 pi f0 t plus 2 pi m over capital M, for m goes 0, 1, 2, m minus 1, and t is in this interval between 0 and t. This is our signaling or symbol interval. So what is happening here? We have m, capital M, different waveforms that are resulting from this generic format. You get one particular waveform by selecting a little m, and that waveform is changed every signaling period. Depending on the size of the m, we can imprint different number of bits onto this signal. M is usually 2 to some power. So if, let's say, m is equal to 8, then I have m equal to yeah, 8, then I have 8 different possibilities for the signaling waveform. That means I can imprint 3 bits per choice of a signaling waveform. Let's demonstrate that this is essentially two-dimensional signal. Let's show that this is two-dimensional signaling, and let's demonstrate what are the basis vectors for this two-dimensional signal. So consider this. I can say that um of t is equal to gt of t, and then this cosine I can write as a cosine 2 pi f0 t times cosine of 2 pi m over n, and then minus, let me put this in parentheses, in a square bracket, sine of 2 pi f0 t times sine of 2 pi m over n. Okay? Now I can separate this into cosine 2 pi m over n times gt of t times cosine 2 pi f0 t, and then plus minus sine of 2 pi m over n times sine, gt of t times sine of 2 pi f0 t. So you identify two things here. There are these which are changing from waveform to waveform, and there are these parts which are same between waveforms. Now, furthermore, this is your cosine, this is your sine. So these are two basis vectors that we're talking about, and these two are essentially coordinates. And if I want to be consistent with my notes, you can put the minus in here. So this here, this first part, this guy is your side 1 of t, and then this guy here is side 2 of t. So, or as a matter of fact, I call this pi 1 of t times square root of energy, and then square root of energy of this g. Now, what is this gt of t? That's a pulse, right? Usually, you know, if you want to think this in the most simplistic terms, this is a square pulse of a duration t that essentially limits the duration of your signal. In practice, as I mentioned last time, for the purpose of not using infinitely wide spectrum, we round the edges of this gt of t. But for right now, we can assume that this is a square pulse, just to make things easy. So I can write this whole thing as a square root of energy times cosine of 2 pi m over m times psi 1 of t, and then plus sine 2 pi m over m times psi 2 of t. Now this is our time domain representation. If I were to, so this is this side. If I want to actually represent this in a vector space domain, signal space domain, then this is just a simple vector square root of energy with two coordinates. One is cosine 2 pi m over m, and the other one is sine 2 pi m over m. Where m goes 0, 1, 2, and so on. So let me go through some examples and illustrate how do we create phase shift keying, and look at what are some of the significant properties of phase shift keying. So some examples. Let's first look at an example, m equal 4. So now I have 4 signals in my constellation. They are two-dimensional. Each one of these 4 signals is going to be built out of the sine and the cosine. And here, for example, I have U1. I can form them this way. Let me look at here, for example. If you look at this expression here, let's substitute m equal to 0. Then this becomes cosine of 2 pi times 0 over 4, which is 1. And then sine of 0 is equal to 0. So my first symbol becomes 1, 0 times square root of energy. When I substitute m equal to 1, then this guy becomes 0, this becomes 1. If I substitute m equal to 2, then this becomes minus 1, and this becomes 0, square root of energy. And then u equal 4, this becomes 0 minus 1, and this is square root of energy. So how does this particular constellation look like? If I draw it here, this is going to be my psi1, which is essentially cosine 2 pi and 0t. And this here is psi2, which is that minus sine of 2 pi and 0t. And my points are located all on a circle, which have the distance from the origin equal to the square root of energy of the particular symbol, of all the symbols essentially, and this is where the constellation resides. So now it becomes clear to understand what do these I mean, it should have been clear up to this point, but it's becoming more and more clear. What this point tells me here is how do I get this symbol waveform? By mixing sine and cosine. It's like generating different light by mixing different chromatic light. I have two colors here at my disposal, cosine and sine, and I can generate all these 4 different signals here by combining sine and cosine in a particular way. This particular constellation is referred to as Qpsk. Q stands for quadrature phase shift key. Quadrature because there are 4 different points in the constellation. There are other versions of this for m equal 4. What is not appealing from this one is that you have every one of these constellation points either has cosine or sine, right? It doesn't have them both. So if you think of in terms of practical implementation, let's say if you try to implement this with some sort of oscillators, that means you're doing a lot of turning on and off, right? You have to turn on cosine and then turn it off, and when you do that, you have transitional periods where nothing responds infinitely fast. So there is a version of this scheme which is also for m equal 4. That's called pi over 4 shifted Qpsk, right? And how do you generate this one? Well, you take this constellation here and you shift it by pi over 4. So this was U1, right? This was U2, U3, U4. So now pi over 4 shifted Qpsk would look somewhat like this. This would be your U1, U2, U3, U4, U3, U4. This is your psi1 and psi2. And you can easily from this diagram, this is again square root of energy, you can easily find out what the coordinates of these guys are. So U1 is going to be square root of 2, is it square root of 2 over 2, right? Or 1 over square root of 2. So 1 over square root of 2, 1 over square root of 2 times the square root of energy. Your U2 becomes minus 1 over square root of 2, 1 over square root of 2 times the square root of energy, and U3 becomes minus 1 over square root of 2 minus 1 over square root of 2 times the square root of energy, and then U4 is equal to 1 over square root of 2 minus 1 over square root of 2 times the square root of energy. So that's an example, 2 examples for m equal 4. They're both referred to as Qpsk, but this one, if you want to be precise, is 5 over 4 shifty Qpsk. And this is by, much more popular version of Qpsk in practical implementations. Now you can continue this process, and I'm going to give you another example. And this is an example for m equal 8. Now in m equal 8, you have, I'm going to start actually from a constellation itself, so that you can see how we generate all these signals. The important thing about Psk, if you haven't figured by now, is that all of the points that you pick in a constellation are residing on the same surface. They're all having the equal energy, right? They're all having equal norm, if you want to see them as vectors. So if I want to form m equal 8, then what I will do, I will take these 2 constellations and put them on the top of one another. So I can pick 8 points like this: 1, 2, 3, 4, 5, 6, 7, 8. Right? So this becomes your U1, U2, U3, and so on, all the way to U8. So U1 is equal to 1, 0 times square root of energy. U2 becomes 1 over square root of 2, 1 over square root of 2, square root of energy, and dot, 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 all the way to U8, which is 1 over square root of 2 minus 1 over square root of 2, square root of energy. Okay? Now, a couple of things. We use these signal waveforms to do signal. If my m is equal 4, how many bits per symbol I can have? 2. So let's say, for the sake of example, that I have 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Right? So located like this. And I can do the same thing here. So I start, from 0, 0. Let's say this is 1, 0, and this is 1, 1, and this is 0, 1. I'm deliberately kind of going a little bit out of order, not completely, but I want to illustrate that you can actually, there is nothing that forces you in any particular way of assigning the bits. There are certain techniques that we use, like what I did here, where you try to assign them in a way so that the adjacent symbols have only 1 bit difference. But there's nothing that orders these things except what you want to do as a design. Here, since I have 8 symbols, I can start from 0, 0, 0, and let's say call this 0, 0, 1, and all the way around to 1, 1, 1, for example, and get 3 bits per symbol in this particular case. So before I continue, I want to talk about a little bit notation, because we already introduced 3 ways, or 2 ways how we can actually talk about these symbols. First notation is, let's call it time domain. And in this notation, I'm going to represent the signal um as I did over there. It's going to be gt of t cosine of 2 pi f0 t plus 2 pi m over capital N. This is in time domain, and this is essentially what happens. This is what I'm sending on a transmission line over my period, signaling period, from 0 to t. Now, second notation that we introduce is our signal space, or vector notation. And here, I'm representing my as the square root of energy times cosine 2 pi m over capital M, and then sine 2 pi m over capital N. Now, this is not what really exists. It actually just teaches me how to form this particular waveform. It tells me that if you want a signal with this signal, this is how much of the cosine and this is how much of the sine you're going to use to form this particular signal. So that's one convenient way of representing. It is easy for us, you will see, and we're going to use it quite a bit because it simplifies a lot of the math. And there's one-to-one correspondence. There is nothing that prevents me from going back and forth. Go ahead.
Excuse me. I have a question. So, for all the m, why is always even number? For example, it's 4.
Oh, why is m, capital M, always even number? Not only that it's even, it is always power of 2 to the n. Why is it? Because remember, what is it that we're doing here? We have stream of ones and zeros, and you're picking up a certain number of those, and you're mapping into one of these symbols. So if you're encoding one at a time, right? Say you pick one, then you send one waveform, and the 0 comes, you send the other waveform. You're talking about just 2 waveforms that you use in signal. One waveform for 1, one waveform for 0, right? And you end up with what we call Psk, where the constellation in that case, how would the constellation in that case look like? You would pick, let's say, this one for 1 and this one for 0, right? So, or, you know, if you, but this is one-dimensional signal, right? Now, if I encode 2 bits at a time, then what can happen? I can have 4 possible combinations, right? I have 0, 0, 0, 1, 1, 0, and 1, 1. So I need n, large n, to be equal to 4. If I'm encoding 3 bits at a time, then I have 0, 0, 0 all the way to 1, 1, 1. How many combinations I have? 8. So I need 8 points in my constellation. If I encode 4, then I need 16, 5, 32, and so on, right? So it's not only that it's even, but it's a power of 2. Going back to our notation, so this is second notation. The third notation, also very common, is a complex notation. And this one is very compact. You know, once you go and realize that this is a 2-dimensional signaling, then we can do something like this. We can call this axis here real axis, and call this axis imaginary axis, and then treat these vector points as complex numbers, because complex numbers are nothing but the vectors, right? It's a pair of 2 real numbers traveling together. So here, I'm going to represent my as square root of energy, e to the j, 2 pi m over capital M, right? So this is even more compact notation of a symbol. Now, a lot of times you're going to see, and somebody's going to say, I'm signaling with this complex vector. It is not that you're sending complex numbers. What is it that you're doing? First you have to go back from here to here, and you do that by Euler transform, right? This is square root of e.g. cosine of 2 pi m over m. That's a real part, so this is this. And imaginary part is this. And then it tells you how much of the cosine and how much of the sine you need to mix before you produce a particular waveform, right? So all of these are equivalent notations. You're going to find them in books. you know, in papers and everywhere, they all mean the same thing. The only thing that really exists is this, but this is how we, you know, represent it, and a lot of times, you know, that simplifies the work that we're doing, or actually allows us to see the clutter of things. Now let me talk about how do you generate these. You know, these formulas so far should explain how you generate phase shift keying. So there's a section of the board. So what do I do here? Do it again?
Keep using the left one.
Keep using the left board?
And half of the second.
Or the wall.
Yeah. So let's do this. I'm gonna limit myself up here. Right. I cannot play it. Alright. So how do you generate your QPSK signal? You have your bit stream coming in here. Bits. And then we have something that usually in schematics we call serial to parallel, which essentially tells you how many bits that are coming in serial you're going to use for parallel encoding. Based on this, how many bits you have, you're actually going to compute how much of a cosine versus how much of the sine you're going to need. And what comes over here is going to be cosine of 2 pi m over capital M. And here you're going to have sine of 2 pi m over capital M. And these are two numbers. What are these numbers? These are actually essentially coordinates in this constellation. It tells you what is the projection on the x-axis or psi 1 axis, and what is the projection on the psi 2 axis. This is still number, and then what you do is you transition into analog domain by feeding this into some pulse filter. This is your shaping pulse. And then you multiply this guy here by cosine of 2 pi f0 t, and this one here by sine of 2 pi f0 t, possibly with minus here, and then you add this to, and this is your t. Okay, so how do we generate the PSK signal? Let me start from backwards. You have this here, which is your carrier. And when we say carrier, what we really have is two carriers in quadrature, meaning cosine and minus sine. These are the same, they're synchronized in time and phase, and they're exactly pi over 2 offset from each other to make them orthogonal. Usually it's one oscillator that has, you know, on a particular hardware that has some circuit that performs the shifting pi over 2, some delay or something that makes one cosine and the other one sine. This here is a shaping filter that actually turns this number into a pulse of a certain magnitude. Let's say for the sake of simplicity that this is a square pulse. So it just says, okay, this is 1 times the square root of 2 times this guy and square root of 2 times this guy. And then you modulate, use this pulse to modulate your carriers in quadrature, and this goes on a particular line. Typically, you know, you treat and you think of this part here is digital, and this part here is analog. So remember in the previous schemes, I said the modulation will allow us to go again from digital world, where we did all the coding and you know, statistical encoding, error correction coding, back to the analog world, because that's the world we live in, and we need to pick the signals that we're going to transfer to the other side. And this is how we do that. We first turn these numbers into pulses, and then use these pulses to modulate our carriers in quadrature. Of course, this part here, one of these, let's say this guy, can be understood as psi 1 of t, and this guy downstairs is understood as psi 2 of t. So even though you have n larger than 2, let's say in this case 8 possible signals or in your signal space, you're essentially signaling with two-dimensional signaling scheme where every one of the signals in your space is a combination of two orthogonal signal sines and cosine. And just the last thing to say about Psk, I already said it, but this is something to remember, that Psk puts all of your symbols on the same unit circle. That means they all have the same energy. Now, why is that important? Think about a signal. This signal has a certain energy and lasts for the duration of t. T is the signaling period. So the ratio of the signal energy to the signaling period stays constant. What is this ratio? Energy over time. Power, beautiful. So the power of Psk signal stays constant over time. This is a precious property when you try to amplify these signals. What happens is, if you maintain the constant power, then you can use cheaper amplifiers because you're not going in a wide range of powers, and you can have amplifiers that are not very, very linear, right? You can have so this is from the standpoint of electronics. This is a cherished product that the signal remains of the constant envelope, constant power. All right. So let me talk about the distance between these symbols. We define something that we call Euclidean distance. Between Psk symbols. Now, let's pick two symbols, Sm, and I'm going to pick the second signal space notation here. Sm is going to be square root of epsilon of energy, the square root of energy cosine 2 pi m over capital N sine 2 pi m over capital N. So that's my first signal. I take a look at another signal, Sn, which is square root of energy cosine of 2 pi n over n sine 2 pi n over n. And I define the distance between these two signals as v and n as a norm of Sm minus Sn. Right? That's the same way how we would define the distance in a let's say complex plane, right? You have 2 points. What is the distance? You take the difference between them, and then you look at the magnitude of that vector, right? What is the difference between them? We know how we calculate. If I have 2 vectors, this is x and y coordinates. How do we calculate the distance? Square root of x1 minus x2 plus squared plus y1 minus y2 squared. So let me calculate the distance between 2 Psk symbols.
Sorry, cos 2 pi, is it m or n?
N.
Capital?
M.
Okay.
This is m everywhere. M is the number of symbols in my constellation. Here m is equal to 8. Total number of symbols, right? N is just an index that allows me to move from symbol here. For n equal, little m equal 0, I'm here. M equal 1, m equal 2, 3, 4, 5, 6, 7, 8, 7, right? But the total number of symbols is a capital N. Right? And I'm picking 2 symbols, let's say this guy and this guy, and I'm saying, well, calculate the distance between them. The way how I calculate distance, just so I look at them as vector. Let's say this is m, and this is n. So this is here Sm, and then here the vector is Sn. And the distance between these 2 vectors is this. The difference between them is this. And then the length of this vector is going to be the the distance between them. The norm of that vector is the distance between them. So I'm going to calculate it over here. And let's derive what happens. I want to point out to a major observation here. So this distance, d, which is the norm of Sm minus Sn, is going to be square root of, let me just do it, square root of the first coordinate difference, second coordinate difference squared, times the taken square root. So it's going to be cosine 2 pi m over capital M minus cosine 2 pi n over capital N, quantity squared, plus sine 2 pi m over capital M minus sine of 2 pi n over capital M, quantity squared, taken square root, and then there's the square root of energy that just comes outside. Now this can be simplified, and let me just spare some writing. You guys know this very well. So there's a cosine squared from here, and there's a sine squared from here. What do they give you? 1, right? So, and there's a cosine squared from here, and there's a sine squared from here, yet another one. Plus the first one, it's 2, right? So this becomes 2 minus, there's a 2 times first times second, and then 2 times first times second. So there's a 2 times, so I have cosine, cosine, plus sine, sine. So that's the cosine of the difference. Follow? So it's a cosine of 2 pi over capital M, M minus N. Taken square root times square root of energy. Now, this can be simplified even further. You know, if I take the 2 out, then it's 1 minus cosine. How do I represent that? That 1 minus cosine of x is 2 sine squared x over 2. Right? So this becomes 4 times sine squared, just m minus n over m times pi. And then taking the square root times square root of energy. And let me just, I don't have it necessarily here, but let's just write this. So this is 2 times square root of energy times the magnitude sine n minus n over n times pi. So that's the difference between two symbols. Now let's take a look at. We have looked at several different Psk schemes. So let's examine how large is this difference for different values of m, right? If I look at m equal 2, 4, 8, 16, and so on. So let's take a look at what happens when m is equal to 2. Where m is equal to 2, the distance between m and n, two symbols, is going to be equal to 2 square root of epsilon energy sine of m minus n over m times pi. Now, of a special interest for us is when m minus n is equal to 1, which means that we're looking at adjacent symbols on the circle, right? When m minus n is equal to 1, I'm looking at two points that are right next to each other if you move either clockwise or counterclockwise. So if I set m minus n equal to 1, then this becomes, and m is equal to 2, then, let me just then put it 2 here. Then this becomes 2 square root of energy sine pi over 2. What is the sine pi over 2? 1. So this distance, mn, is going to be equal to 2 square root of energy. Now when m is equal to 4, dmn becomes 2 square root of energy sine of m, sorry, little m minus n over 4 times pi magnitude. If m minus n is equal to 1, then dmn becomes equal to sine over pi over 4 is square root of 2 over 2 times this square root of energy. So this is square root of 2, 1.414 times square root of energy. Let me just take it a couple of m equal to 8. Then this dmn is going to be 2 times square root of energy sine of m minus n over 8 times pi. And if I set m minus a equals 1, then this dmn becomes 0 times 6, 7654 times square root of energy. And in the last case, when m is equal to 16, dmn is equal to 2 square root of energy sine m minus n over 16 pi. And when I set m minus n equal to 1, then I get that the distance between the two adjacent symbols is going to be 0.3902 square root of energy. Now, if the energy is kept constant, so this square root of energy is the same, which means the power of the signal is kept constant. Then as I increase the number of symbols, what happens to their distance? Their distance becomes smaller and smaller, so they become closer to one another. The circle becomes more and more congested, right? The circle is the same size because I'm fixing the energy, but since the number of points is larger, these points become closer. If I want to maintain the same distance between these symbols, what do I need to do? What do I need to do to maintain the same distance between the symbols if I'm changing m? As the m becomes larger, my energy needs to become larger, and I need to what means essentially I need to increase the power of my transmission, right? Now, this should resound a little bit familiar, right? Because we just went through capacity analysis, right? And what is it that one of the messages from there is that there's a fundamental trade-off between data rate, between signal to noise ratio, and the occupied spectrum, the capacity, the bandwidth of your channel. From previously, we already know that the spectrum occupied by the signal, digital signal, is proportional to the symbol rate, or it's inverse proportional to 1 over t. So by the same trade-off is kind of hidden in these equations here. If I try to increase the capacity of my, let's say I'm signaling over the channel that has a certain band. If I'm trying to increase the capacity or the number of bits that I'm sending through this channel, then one of the easiest way to do that is I'm going to higher modulation schemes. I'm actually increasing the number of symbols, number of waveforms, and every one of these waveforms is packing more and more bits. So through a fixed channel, I'm increasing the throughput, and the price that I need to pay for that is I need to increase the power to maintain the distance between these symbols. Right? So the same, just monitor this as we keep on going forward. We'll come back to this once we start calculating the bit error rate, and there will bit error rate and symbol error rate, and that's where this trade-off is going to be even more apparent. Any questions on PSK? Go ahead.
Sure, when we increase the server, the time period doesn't stay the same, does it?
Time period, the signaling period.
Yeah.
Okay. You can, this is the extension of what I just said. The extension of what I just said. Let's say you have zeros and ones coming in here, right? Now, let's assume certain bit rate, which would result in a certain duration of this symbol. This symbol, or let me write it the other way around. Let's say that this is TB, and therefore the bit rate is going to be 1 over, or exactly equal to 1 over TB. So let's say you're signaling at 10 kilobits per, or 1 kilobit per second, which means that your bit is 1 millisecond long, right? You have we have thousands of them in every second. Now, at this point, you transition from bits here into symbols. And every TS, you're picking one symbol, right? One of the points in your constellation, let's say these guys. And let's, for the sake of example, assume that I have 8, so m is equal to 8. So, how do I do that? Well, I'm going to pick 3 bits at a time, right? And I'm going to turn this into one of the symbols. So if I'm using m equal 8, how large my TS is going to be? 3 times TB. How about my RS? My symbol rate is going to be 1 over TS, which is going to be RB over 3. So I'm signaling 3 times slower on my channel than what my bit rate is. Okay? Now, what do I know about my bandwidth? Bandwidth is proportional to your rate, to your signaling rate. So here, the bandwidth is proportional to RB, right? Here, the bandwidth required is proportional to your RS. Right? Or ideally, in your book they say bandwidth is whatever is the rate divided by 2. That's an ideal scenario, but I kind of use more relaxed where I say it's proportional to this. So let's start backwards. Let's say if I give you that the bandwidth is equal to, let me think of a good example. Let's say bandwidth is equal to 10 kilohertz, right? And if my RB is equal to 40 kilobits per second, then what kind of signaling scheme do I need to pick? Can I use BPSK? I have to use QPSK. Why? Because from here, I deduce that no, not even QPSK. Let's think about it. From here, I deduce that my RS needs to be 10 kilosymbols per second, right? If my RS is 10 kilosymbols per second, that means for every 4 bits, I'm going to have one symbol, right? So what kind of scheme I have to be using here? If I restrict myself to PSK, 16 PSK, right? So I have to have 4 bits per symbol, which means 16 PSK. Theoretically, you can see this way you can fit pretty much any throughput into any band. But what happens when I go to 16 PSK? My symbols are really, really close, and even the smallest disturbance would turn one into the other. So I have to make sure that my signal to noise ratio is really, really high. And that I have to pay in power. So this is a fundamental trade-off where I'm in a channel here, I'm putting a really high bit rate, but I have to do that, I have to maintain very high signal to noise ratio. And that's what Shannon's formula is teaching us. So that's not news to us. Okay. These things are very important, these relationships. You know, we're going to go through them in various examples, but this kind of fundamental trade-offs is what you need to leave this class with. You need to have a good intuitive feel about, you know, and understanding what's a symbol rate, what's the symbol time, bit rate, bit time, how are these related, and how does all of this relate to your constellation points and number of bits per symbol that you use in your constellation. Let's, so this is Psk. As I said, the key point about Psk is that all symbols are on a unit, on a circle of the same energy. This makes it nice because the envelope of the signal is constant, and therefore the power of the signal is constant. But, you know, even from these preliminary considerations, you see that there's one fundamental flaw here, and this is that if I'm given this much of a area in my signal space, there's a better way to redistribute these points to maximize the distance between them, right? I don't want to jam them all on the same energy circle. I can actually spread them more in this space. So this is how we get to the concept of the quadrature amplitude modulation. Quadrature amplitude modulation is actually more general than this. It is it's the most general, I would say, what we call linear modulation scheme, which is this kind of two-dimensional signaling. It will, as you will see, it will include Psk as its special case, but it will be more general and it will allow us to select some additional points, and therefore it has potential of being more optimum from, let's say, signal to noise or bit error rate standpoint. So let's just talk about quadrature amplitude modulation. So quadrature amplitude modulation. So here's how quadrature amplitude modulation waveform looks like. Um of t is going to be equal to some am g t of t times cosine 2 pi f0 t plus theta n. So unlike Psk, in which case we just changed the phase here and kept everything with a constant magnitude, here you have 2 degrees of freedom. You're changing the magnitude here and the phase of your carrier. Let's first demonstrate that this is two-dimensional signal in a manner similar to what we did for Psk. So consider now that I can write um of t as am gt of t times cosine 2 pi f0 t times cosine of theta n, and then this in a square bracket minus sine of 2 pi f0 t times sine of theta n. And this I can rewrite as am cosine of theta n times gt of t times cosine 2 pi f0 t, and then plus am sine of theta n times minus gt of t times sine 2 pi f0 t. you recognize that this part here is your psi 1 of t times square root of energy, and this part downstairs is psi 2 of t times square root of energy. Or you can, I'm writing this square root of energy here to be mathematically correct, because psi 1 and psi 2 are supposed to be unit vectors, right? So they have the unit energy. But a lot of times you just write, these are my two basis vectors, psi 1 and psi 2, implicitly knowing that, that they are scaled by the appropriate energy. Now, taking these two vectors into account, then I can actually rewrite this actually, let's call this UMN, because there are two, M for the magnitude and N for the phase. So UMN of t, I can write as AM cosine of theta n times square root of energy sine 1 of t, and then plus AM sine of theta n times square root of energy times sine 2 of t. So that's our time domain notation that teaches us essentially how to build quadrature amplitude modulated waveform. If I take my cosine vector and sine vector, and I'm multiplying cosine by the first coordinate, sine with the second coordinate, I can pretty much pick any point in my constellation space and declare that as a Psk signal. Now, two other representations, I can, so this is my first representation here. Second representation, I can say that UMN now as a vector is a square root of energy, and then AM cosine of theta n, AM sine of theta n. This is essentially our vector notation, or I can say in a third notation, UMN is equal to square root of energy, AM e to the j theta n. So this is a complex notation, and all of them essentially show us this particular waveform. All of them. So the total number of symbols is essentially m times n, where m is the number of amplitude levels and then n is let me do this. Call this n amplitude times n phase. So n amplitude and the number of phase possibilities. And the total number of symbols m is going to be NA times NP. And usually this m is chosen as 2 to the n, just like in the case of the of the Psk modulation schemes, right? You're going to pick the number of symbols in your constellation to be 2 to the n, 2, 4, 8, 16, and so on. But you're going to distribute them between different number of amplitude levels and different number of phase levels, which are allowed by the Qpsk by QAM modulation scheme. So what are some examples? I'm just not gonna write coordinates anymore. Just draw the points. Let's say I pick one amplitude level and 4 phase levels. So I may end up with something that looks like this. Right? So this is 4 QAM or Qpsk, right? So you can see that the phase shift keying is a special case here. I'm picking here n amplitude is equal to 1, and n phase is equal to 4. So I have 4 different phases and 1 amplitude. Let's take a look at 16 QAM. If I were to use 16 on in a Psk, that would be 16 points that I cram on that circle of a given energy. But here, I can do something like this. So this is psi 1, psi 2. How many different amplitude levels do I have here?
4.
Is it 4? It seems to me 3 as well, right? There's 1 here. Okay. There's 1 here. And then there's 1 here. Right? So there are 3 different amplitude levels, and then I have a few different phases. Right? This is 1, 2, 3, 4, and then I have 4 plus 8 plus 4 again. Right? Is it even divisible? Something is not correct, right? Yeah, because these are on the same phase. So I have, let's say, how many different phases I have? 1, this is 2, this is 3, this is 4. And then I have 5, 6, 7, 8, 9, 10. And so how do I get 16? I'll need to look at that. But so by doing QAM, you can see that you can pick pretty much any point in this constellation space, and therefore your Psk is essentially this one version of the QAM modulation where you just happen to be picking all the points that are residing on a circle of the same energy. How do I make a modulation? So QAM modulate. You start the same way. You have your bits, then you have your serial to parallel converter, and from here you're going to calculate your AM cosine of theta n, and here's AM sine of theta n. And from that you have your pulse, GT of t, then cosine 2 pi f0 t, sine of 2 pi f0 t, that's going to be minus, and then you add these two, multiply n, to generate your u and t. Now, what can you tell me about this module? It's exactly the same as the one that we use for PSKs. So, a lot of times we call this a quadrature modulator, or just modulating the carriers in quadrature, and it's essentially the same piece of hardware that you're going to use. You can use for PSK, or you can use for QAM, and it's essentially the same. Both of them are picking the points from this constellation plane, and both of them are essentially performing a mixture of the two basis vectors. One is your cosine here, so this is your psi 1 of t, and the other one downstairs is your psi 2 of t. So both Psk and QAM modulation can be seen as two-dimensional signaling where you're mixing cosine and sine, and what you're doing is you're actually calculating here what is the proper mixture, and that corresponds to a coordinate that you have picked in the signal constellation space over here. Now, in a lot of places when they show modulation schemes that they're using, they're actually showing you this. And you can see, you flip any journal, they're going to show you a mapped constellation, which is essentially representing this, right? This is what happens in the background, because we got to really create the time domain signals, and the way how we do that is by mixing proper way of proper quantities of the sine and the cosine. Let me give you some homework problems. These are going to be 7-3, or let me actually start with 7-1, 7-3, 7-4, 7-5, and 7-6. We're in chapter 7, so these are problems, exercises, some of the stuff that I've been covering in class. Any questions? Go ahead.
In the quant, is the difference between the levels should be the same?
Between what levels?
Like level 1 to level 2, the difference, and also level 2 to level 3, is the difference of every levels should be the same?
Oh, between the distances between these, right?
The circle.
Oh, the circles are
The difference between the circle, the distance.
You have actually flexibility to make it however you want. I mean, there is nothing that's why quant is general in the sense that it really, you calculate two numbers and do the mixtures. Practically speaking, in these modulation schemes, you have some, let me just draw it, because that's how I remember it, then we'll calculate what those circles are and answer your question. When you do the, let's say 16 quant, then what, this is A, this is 3A, this is minus A, minus 3A, this is A, 3A, minus A, minus 3A. So that's how you create the grid. So let's just see what, you can see what this is this is two palms kind of cross multiply. You have palm across this axis and pulse amplitude modulation across this axis, right? And keep the distance between symbols the same. So let's see here. What's the energy of the first circle? This thing here. So square root of energy 1 is square root of 2a, right? A squared plus a squared square root of that. The square root of energy for the second circle is this guy here, right? And this is equal to square root of 3a squared plus a squared. So 3a squared, so this is 9a squared, plus a squared, which is square root of 10a. And then square root of energy 3 is going to be square root of 3a plus 3a, right? So 3a squared times 2, which is square root of
18.
This a is outside, right? Square root of 18a. So the distance is not the same, right? To answer your question, what you're really trying to do is this, and this will come into play later when we talk about the nodes. But you can understand it even from, with some minimum explanation here. This is the constellation point that you use. When you send a signal on the other side, what noise will do to your constellation point, it will move it somewhere in its vicinity, depending on how large this noise is. And what you're trying to do is make sure that these disturbances are least likely to produce errors. And what you accomplish that by making sure that in every direction your nearest symbol is approximately the same distance, right? So that's the design goal. And then that results in a particular constellation here. We'll come to that when we start calculating in detail.
Okay.
Right?
So, but now our signals don't all have the same energy, and then this is bad for our power amp?
Yeah, exactly. It's bad for our power amp, but it's more efficient in terms of for an average power, how much of the information you're transferring, right? Because here, you're utilizing your constellation, your signal space much better, right? Let's say this is 16 here. Imagine if I were to cram them all on the circle, right? The distances between them is going to be much smaller. So I would have to use much higher power to maintain the same probability of error. Here, with a lower power, I can maintain the same probability of error, but I pay that to the amplifier.
But so that means we just need a linear amplifier.
More linear amplifier that is amplifying the same, regardless if the signal is of this power or at higher power, right? What happens to amplifiers is this. They all have characteristics that look like this, right? This is Pn, and this is P out. And then if you operate within a certain small region, let's say here, then your amplification is constant. But if your signal is changing its power, then amplification in different portion of this curve is going to be different. And that creates problems. So that means if you're using QAM or higher modulation scheme, your amplifier needs to be really linear, like 64 QAM would be 8 by 8 matrix, right? So it needs to be linear over a much larger range of powers, right? Okay, any other questions? Okay, that's it.